Okay, so let me repeat part of them again. So now when you have a boundary condition, like essential and natural type boundary condition, then especially natural type boundary condition like that one is going to give you a column vector, all right? Because test function and known value, this is known value. But in your project, when you have a convection boundary condition, then unfortunately, this is not a given value, that's the function of u. So in especially convection, that's going to be linear function of u, ax plus b. So in other words, this is not fully given. Then what happens is that if you plug into your boundary integral expression, so du dn is replaced by au plus b, then you can break that into the first term and second term, and a and b are constant in this case. So if you look at the first term, then you got w and u, test function and trial function. So whenever you have a product of test and trial function, it becomes the matrix. And second term, you have only test function only. B is going to be constant, so no trial function. That's going to be column vector, right? So if you have a domain, whether you use rectangular or triangular shape element, you are going to have a node like this. So if you use a triangular shape element, then the domain integral is going to be 3 by 3 matrix. Okay. If you use rectangular element, domain integral is going to be a 4 by 4 matrix because you got 4 degree of freedom or 3 degree of freedom, right? But this boundary integral is going to be along the boundary, either this one or that one or that one. So along the boundary, what? Each element has only 2 degree of freedom. So this is going to be 2 by 2 matrix. Okay. And this also 2 by 1 column vector. So that's the key point in your first project, right? And your textbook has some coding for that. So if you check that, then you can find out some of the information in the book. All right, that's all I can give you. Any question? All right, then couple more just announcement to make sure. So as scheduled, we are going to have our first exam, midterm exam on February 10. And so we don't have a class on February 10. So I'll give you exam on February 10 around noon at this Pacific time zone. All right. So I'll give you around noon and I'll give you the handout by email and then collect the noon of the next, the day Wednesday. Okay. And that's it. And also this Thursday, the day after tomorrow, I have a meeting to attend just before the class so that our class is going to start a little bit later. So we are going to have a class at 2:20 instead of 2 o'clock.
This Thursday?
Yeah, this Thursday, because I have to attend some the meeting. So I'm going to also send that email to everyone because a couple of people are missing here, as well as folks in distant learning. Usually they watch the recorded video. So I'm going to send that email to confirmation. Okay. Any question? So far so good?
We're just emailing it back in on Wednesday, correct? Or emailing it by Wednesday, correct?
You mean the exam? Yeah, so you're gonna return by email or you can bring it the hard copy. Either one is fine, especially people in here, you have an option. right? Yes.
I have a question about the project. For the submission, will you just take a MATLAB script or would you like a write-up to go along with it?
So when you say write-up means that you cannot just submit the MATLAB code itself. That's not the complete the report. You have to attach the codes definitely, right? But you have to show the formulation and derivation of the the matrix. Some of them, of course, in the book, but also something different as I talked about, it, like this convection boundary condition, and then also discussion of the result, whether it makes sense physically. So you have to have those kind of the write-up in the report, not just simply this is the program, that's it. So that's not the report, at least in my class.
Okay, thank you.
You're welcome. Any other question? All right, then let's go back to our the regular class here. So we started chapter 8 last week, and now we are talking about multi-degree of freedom per node. So the first example is again one-dimensional problem, ODE, and beam bending, the equation, and the boundary, differential equation for beam bending is fourth order, not second order. We talk about second order so far, but that's the fourth order. And then if you have a fourth order, boundary condition is up to third order derivative. That's the nature of differential equation. Then we have either U is going to be this deflection or lateral displacement, and theta, which is going to be first derivative of U, which is going to be slope, or second derivative with multiplied by EI. EI is the beam rigidity, how stiff the beam is. E is elastic modulus. I is the second moment inertia cross section. So multiplied by that, that's going to be the moment. So which is going to be also another boundary condition. And then third derivative, and which is related to the shear force. That's going to be also another potential boundary condition. So you have a four possible boundary condition, and for this the fourth order, and you need to have four boundary condition to complete the problem, okay, for unique solution. So usually, not usually, left side you have a two boundary condition, right side you have a two boundary condition. So for example, simple support, either left or right, doesn't matter. At the simple support, this deflection is zero and moment is zero. Why moment is zero? Because this is going to be free to rotate with the pin joint, so that the moment is zero. When you have a clamp, then displacement is zero and slope is zero. And when you have a free, nothing applied, that means here the moment is zero and shear force is zero. So those are, typical boundary condition we are going to deal with. And now in terms of finite formulation, again, using the method of weighted procedure, then apply this one, just the standard method weighted procedure. Then you can see that test function, strive function, they require different order of derivative. So we are going to apply the weak formulation so that we can weaken the requirement, because requirement is going to be governed by this one in Galerkin's technique. So we apply integration by part, then still first order derivative, third order derivative. So you apply integration by part one more time, then finally you got second order derivative, both test and strive function. So we stop there. If you do one more time, then we are going to swap that derivative, so the W is going to be third order, U is going to be first order, so then still dictated by the third order of the W, so it doesn't make sense. So we are going to stop at this point, okay? So whenever you have an even order derivative, 2, 4, 6, 8, usually we don't have that kind of higher order differential equation, but let's say if you have such high differential equation, then we go until they are equal, when this is going to be even order. But if this is going to be odd order, like a first, third, or fifth, like that one, then there's no way you can make that equal. So you have to stop when the difference is going to be minimum. For example, if it's gonna be third order, then this becomes first order, this becomes second order, then you stop there, because after doing that, it does not change much, so we are gonna stop whenever they are close enough. Okay, so that's what you have to do for weak formulation. Then once you have a weak formulation, then those are the boundary condition. L is the right side, 0 is the left side of the boundary condition. And those are the domain integral. And this is also domain integral when you have a load applied to the member, the beam. And now to look at that one, look at this evaluation. So we talk about C1 continuity. That means your shape function have to be continuous, not only U and W. The reason I talk about it that beam deflection, the proper shape of beam deflection have to be, for example, if this is the beam and apply load and have to be like this. So not only deflection is continuous, but slope have to be continuous. You cannot have this kind of deformation, right? Like a sharp corner in here. This deformation occur when you have a second order differential equation. Second order differential equation is going to be for the string. If you have a thin string, and if you push the bottom, then you can see some kind of triangular shape that is, governed by second order. Then that is correct. Then we don't have to require the slope continuity. But for the beam bending, you have to have not only deflection but slope have to be continuous. So what you have to do, you introduce slope as a nodal degree of freedom that guarantee that continuity of the slope from one element to the next element. So each node you have now 2 degrees of freedom, deflection and slope. Same thing, deflection and slope. So I have a 4 variable, then 4 cubic polynomial. And when you have a cubic polynomial written in this way, then now slope is derivative of deflection. Slope is derivative of deflection. So you have to take a derivative with respect to x, you got that. Then you evaluate both deflection and slope at x equals 0, x equals L. That should be U1, theta 1, as well as U2, theta sub 2. Then from there, you find generalized coefficient C0, C1, C2, C3 by inverting this one, and then plugging that into that expression for C. For this one, you come up with the following shape function. Okay, and the nature of this shape function is shown here, the characteristic, so that if you plot it, the first shape function, not only magnitude is 1, but slope have to be 0 here, as well as slope have to be 0. So value is at 1, but 0 slope, 0 slope. Same thing, the third one, magnitude is 1, but slope is 0, 0 slope. But the second one is 0 value at both ends, but slope is going to be 1 here and 0 slope. And the fourth one, also 0 value, but slope is 1 on the right side and 0 on the left side. So that's going to be the proper shape function. And then to represent the rigid body motion, we see that H1 plus H3 is going to be not equal 1, but not all of them is equal to 1, like a C0 type shape function. And then plugging that shape function into here with the second derivative, because the second derivative, then we came up with element matrix. So this we call element, especially stiffness matrix of beam bending. 2 noded element beam bending is going to be stiffness matrix. EI is again beam rigidity. L is the length of the member. So you can get that. So you can calculate this one over and over for every element. Even element length is different from one element to the other, doesn't matter. But, and this, the loading function, the Q is going to be applied load. So if Q equals 0, then of course nothing you can do. But otherwise, you have to evaluate that. W is going to be again same as shift function in Galerkin's technique. So H1, H2, H3, H4, and Q should be given. And if this is going to be constant, the pressure loading, then if you plug Q is going to be constant, you evaluate this H1, H2, H3, H4 integration from 0 to L over the element length, then you came up with this value. And what this physical meaning of this, the first one is force moment. Okay, in other words, if you look at this, displacement, the left-hand side displacement, then the right-hand side, this column vector indicate the force, displacement force. This is going to be slope, that's going to be moment. Displacement, force, slope, moment. Why they have to be like that? Because force time displacement is what? Force time displacement is energy, right? The work or energy. And moment times slope is also the work. So they call energy conjugate. In other words, every product should get same meaning of energy cell or work. Okay. So force moment, displacement slope. Okay. So anyhow, so this is represented in this kind of way. In other words, if you have a loading like that one, this is, the true loading. But in terms of finite element context, you cannot apply load other than at the nodal point. So you cannot put the load, at this location. Everything have to be represented at the nodal point. So this is represented at the nodal force and nodal moment. And the physical meaning of this force and moment is, I explained that when you have a, beam clamp at both ends, and let's say apply opposite load of this Q nut to apply, downward direction, then the supporting condition at the right side, if you solve this statically indeterminate problem, then reaction force and reaction moment is exactly the same as this one. So in other words, those values are not just arbitrary, that has some physical meaning. So in other words, that really represents the reaction canceling out this uniformly applied pressure. So that had to be represented at the nodal point, right? Okay, then continuing from there today, if you happen to have, this is one element, then if you happen to have a force applied in here, so this is going to be P, like a concentrated force. Okay, how do you calculate equivalent nodal force and moment at the nodal point using the finite element formulation? So this is the same as before. Now, question is, how do you represent this one mathematically? Concentrated force is using delta function, right? Whenever you concentrate quantity, they're represented by the delta function. So if this is going to be x naught, then P delta x minus x naught. So when x is x naught, this is going to be 1, so equal to P. Otherwise, it's going to be 0. So that's the definition of delta function. So you take P outside because P is going to be finite value. Then what's the property of delta function? The delta function is, as long as x0 is within the domain, then evaluation of this one at that location, x naught, so h1, evaluation x naught, h2, x naught, like that one. So that's going to be your column vector, right? And usually the simplest way is that if you have a beam, if you have a beam and I have a concentrated force, for example, here like this, right? Then to do, solve this problem is simplest way is going to be put the node in here. Regardless how many elements you are going to do, put the node here. Then this force is represented at the node, this force is represented at that node, right? But if you do not put the node at the location of, the force, then you have to do this calculation. Okay? And this calculation also represents exactly these cases. In other words, that x0 happen to be equal to either this point or that point, that means force is applied either this point or that point. So this is very general. And some simple cases of the loading, like a constant loading, concentrate force, or concentrate moment, and linear loading, okay, linear pressure loading, using the same formula that is going to be expressed in this manner. So those are the column vector of this in bending with equivalent, the loading. Okay. Otherwise, as long as you know that Q, any given function, then you have to evaluate this one, H1, H2, H3, H4 multiplied by Q and integrate this one. That will give you your right-hand side column vector. Any questions so far? Then go ahead.
Where was it that you apply those equations that you just showed for the different loadings?
So this different loading, this different loading, this is going to be the the column vector of the element. So if you have, let's say, beam and I have concentrate force and I have this kind of force and I have this force, right? Then first of all, you have to do the mesh. So as a simple, case that, let's say I have a node like this, right? So 1, 2, 3, 4, 5 elements. Then this will, become the, so in other words, if you construct a matrix, so this is going to be U1, theta 1, U2, theta 2, U4, theta 4, U5, theta 5, U6, theta 6. So I have a 1, 2, 3, 4, 5, 6 nodes. So that U1, theta 1, U2, theta 2, U3, theta 3, U4, theta 4, U5, theta 5, U6, theta 6. You got so this, matrix equation. So that's going to be 12 by 12. So in other words, you construct the matrix 4 by 4, 4 by 4 by 4. So that's going to be something like this. So 12. But the force vector is this one. Will go to U2, correspond to here. This value goes here. Of course, this is the opposite direction, so minus of the magnitude, right? And now this one, which is going to be this value. This value, of course, the direction is opposite, so you have to be minus sign in here because this is defined upward positive, so minus sign of that. But this 4 by 1 column vector goes into U sub 3 to U sub 4, so here, 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 here is going to be added to here. Okay, and then the last one of this one is this, but again minus sign, so you have to put minus because this the loading is opposite direction, and that goes U5, theta 5, U6, theta 6, so it goes into here, added into here. Okay. Now, if someone said, I'm gonna increase the mesh, so I'm gonna put additional load in here. Right? I'm gonna put additional load here. Then how do I solve that problem? In this case, you have to divide this is, oops, let's put this there, but not there. This one and this one, because this element is going to be this load, this element is going to be this load, right? So this one is same as this one. Again, sign is opposite, but same as that. Huh? What about this one? This one, trapezoidal shape, what you can do? Break into two pieces, right? So this come from here, again, an opposite side, and this come from here, again, opposite side. So you add them together, that's going to be total column vector, right?
You just add them,
This one, you have to add both of them into same column vector.
be like that equation plus that equation, like,
Yeah.
it's gonna be like that.
Now, so we look at this term, element matrix, stiffness matrix, and element force vector, they call element force vector. Even you have a moment, but they call element force vector. So we talk about that. And then what about these two terms? That's what we are going to talk about right now. So those two terms are shown in here. Yeah. Now, I said this term, EI times saw derivative deflection is equal to shear force. That's the shear force. Okay. And EI times second derivative of the deflection is equal to moment. So you replace this one by shear force, this one by moment, and then evaluate at the right minus evaluate the left. That's what the meaning of this symbol, right? Right, upper minus lower, integral limit. Same thing, this is upper minus lower. And now you are going to put the zero terms, left side evaluation, put together, and then right side evaluation put together. So this is on the left side of the boundary, this is the right side of boundary. So in other words, the first term is evaluated at the first element, which contains the left side boundary. And this is evaluated at the last element, which contains the right side of the boundary. So if you look at this one first, right? Then again, Galerkin's technique, W is equal to the shape function, H1, H2, H3, H4, and that should be given value or unknown value, shear force, either known or unknown. And this one is also a derivative of the shape function. The test function derivative is equal to shape function derivative in the Galerkin's technique. So again, derivative 1, 2, 3, 4 shape function, and evaluation is 0. M0 is going to be either known or unknown, boundary moment at that location. So if you look at the property of this shape function H1 at 0, if you remember the property of the shape function here in this slide, H1 is 0 H1 is 1, and the rest of them are 0, at x equals 0, all 0. And what about the derivative? Derivative, look at this derivative. Okay. H1 derivative 0 is 0. H2 derivative, where is H2 derivative? 0. H2 derivative 0 is 1. And H3 derivative 0 is 0. H4 derivative at 0 is 0. So you get that. Then what do you get? If you put together, this is going to be minus V0 and N0 like that. Okay, N0, 0. And now this is, again, going back to this one. This is in here on this side, right? And when you write an equation, then usually we want to write an equation like this. A, X is B. In other words, all the column vector to the other side of equality. In other words, this one remain on this side. All of them goes to the other side. So to have a formula AX equal B here, then means when you move this one to the other side, then sign is going to change such that V0 minus M0. N0, 0. When you add them up to here, have to be added like this one, because you have to go to the other side, sign change. And then I'm going to explain what the means of this one in a minute. Then let's look at the this one, the right side. So the right side is boundary is going to be same as previous, and then again the test function is replaced by the shape function. At L means that at element level, that's going to be lowercase l at the element side, right side. And then this is going to be the derivative. And then evaluation at the right side of that. And this is going to be either given or not given. And if you look at this function, then everything is going to be 0 except this. So that's going to be only 1. And if you look at that, everything is going to be 0 except this one. So you get that too. 0, 0, VL, and negative ML, like that. But also, if you put this one to the right side, then what happened? This one have to change the sign. 0, 0, minus 3L and positive ML. Okay? So when you construct the matrix equation of this one, and then apply this boundary condition, what is going to happen is you got the big matrix equation, right? Then the first U1, theta 1, etc., and then last one UN, theta n. Okay, last note. Then this is going to be V0, negative M0, and blah, blah, whatever. And this is going to be negative VL and positive ML. Okay, so that's the left side shear force moment and right side shear force and moment like that. Then you're going to see that this sign is a little bit confusing to have to remember all this sign, you know, negative moment and negative shear force in here. And the bottom line is, no, you don't have to worry about that one. The reason is following. When you develop the beam bending equation, okay, we develop that's the positive shear force and that's the positive moment in our sign convention. Okay, so this is the shear force and that's the moment. That's the sign convention you use to develop this beam bending equation. All right, but in terms of finite element context, we do not look at this right or left like that one. So we look at that as a node. Every node. Right? Every node. So at every node, if deflection is going to be upward, we define U and theta, right? We define deflection upward positive, and this is positive, counterclockwise, right? Then this force and moment, have to follow the same direction to produce the positive work or positive energy. In other words, that the force at every point, that's positive, and that is positive moment. Positive force and positive moment at every point. So if you look at this one, compare with that one, then you see this, the moment in your sign convention is opposite of final element, right? This is the clockwise, this is the counterclockwise. So that's why you got the negative sign. And on the right side, I have force upward positive, but shear force is downward in sign convention. So that's why it becomes minus sign. So bottom line is that forget about this, okay? Every point, the force, same direction of U, positive. Moment, same direction of the rotation, positive. That's all you have to care, right? So you don't have to worry about this one anymore. So every nodal point, either left side, right side, doesn't matter. Positive sign convention of force moment is going to be like that one in terms of finite element context. Because every nodal point, you have defined displacement and slope in this manner, so same direction. Make sense? Any question?
That's just how you said it to me, that.
Hmm?
So you're saying that the direction of the force and the moment depends on how you.
How you define the displacement and slope.
Okay.
Because the product should be the work, positive work, right? Then force and the deflection should be in the same direction, right? Otherwise, it's going to be negative one. So, any question?
Earlier, when you were talking about I think I saw at the top of the page, it said consider boundary terms.
Mm-hmm.
And it was like this big part where it had the WEI, which then you change it for a V and then a W.
Mm-hmm. Like this one.
Yeah.
Mm-hmm.
So where did that equation come from? Because it seems.
So-
it looks like that.
By in the derivation of that beam bending, so you take a derivative of that is slope, right? And if you take a second derivative, right, and multiply by EI, that's going to be the moment. And then Tm, Tx is shear force. We know that. So plugging this one into here, then assuming EI is going to be constant, then that gives you EI, and the third derivative is equal to the shear force.
Well, where did that minus, it's like those two terms are being subtracted to each other. I don't know where that came from.
This one,
On the top left. of
top
the
left
page.
here.
Yes,
So this one,
it's like that whole thing.
yeah, this whole thing, EI, third derivative is shear force.
Oh, yeah, I understand the relationship between like that
Uh-huh.
second and the third derivative, but why are you subtracting the shear force minus the moment there?
Oh, no, it's not subtracting. This is gonna be evaluation at 0 to L, this is also evaluation, so two separate terms. I mean, minus sign happen to be there in the derivation, but don't look at the minus sign. So this is gonna be evaluation of this, so this is the work. The force, I mean, displacement times the force, right? So work, the top, the right side minus left side. And also this one, work, right side minus left side. But minus sign happen to be from the integration by part, okay? So that doesn't have a physical meaning, just from the mathematics. So those are two separate terms. We are not substituting this one minus that one, it's not like that.
So you're saying that this is just an evaluation over the whole thing for the shear force and an evaluation of the whole thing in terms of moment.
So this is evaluation at only two extreme boundary points, not along the length of the beam, right? This is the boundary integral. So evaluation at the right, evaluation at the left. Yeah, so that's going to be only a specific, this one-dimensional problem is boundary is going to be the point. So this is evaluate at specific point of the right side or left side of the boundary.
That makes sense.
Okay, any other question? All right, then let's take a short break and then continue from here.